And thank you everyone for joining us for our fourth webinar in the UFFCS America, Latina, and FOCO series from the IEEE UFFCS Latin America Outreach Initiative. Before we get started, I wanted to inform you again that this webinar is being recorded. We're excited to have you join us today featuring the topic piloting a Tele-Ultrasound Diagnostic System for deployment in rural areas of Peru in RBTU Brazilian platform for ultrasound research. I wanted to remind you to remain on mute until you have a question and you're called upon. And while we introduce the speakers, I invite you to our Zoom questions that we're going to have appear now. Just give me one moment. And then for this webinar, a talk will be given by Benjamin Appen, followed by speaker Eduardo Costa and Amanda Martinez. Moderating our session today is Jean-Luc Jennison. During the webinar, please type your questions in the chat box at any time. They will be answered during the Q&A session of the webinar. If you would like to ask a question during the Q&A session, please raise your hand, switch on your camera, and unmute to ask your question. Automatic closed captioning will be available. Please press the closed captioning or CC button and choose show caption to enable it at any time during the webinar. I would now like to introduce you to the organizing committee of the Latin America Outreach Initiative. We have Hermes Kamimura as the Latin America Outreach Initiative Chair. We have Sophie Morse as the Volunteer Engagement Committee member. We have Andrea Polido, a Latin America Outreach Initiative volunteer. Patricia Cardoso de Armande, a Latin America Outreach Initiative volunteer. And then Stephen Lee, who has been video editing all of our videos for the webinars. Patricia and Andrea will translate typed questions from there and that are asked in Portuguese and Spanish and will be translated to English for the moderator. And then Hermes with the announcements.
Hello, everyone. Welcome to our fourth America Latina in Foco webinar. My name is Hermes Kamimura, and I have some announcements for you before we start the talks. Can you share the screen? We have to close the poll, right?
Yep. Just give me one moment, please.
Yeah.
Okay.
So I don't see
It's having technical difficulties again. Just give me 1 second. I apologize.
So I just want to start saying our Latin America Ultrasonic Symposium is fast approaching, and I will show some of the news we have for that. We are planning. We are very proud of this event, and we hope that you can join us. We can go straight to the slides too. So this is actually the old one. I sent you the updated announcements. Do you have this?
Yes, give me 1 second.
Yeah. Sorry, everyone. And in the symposium, we will have interesting panels, Dr. Michael Tanter and Dr. Carlos Negreira presenting joint talks showing more than 2 decades of collaboration between Uruguay and France. Similarly, we will have Dr. Koen van Dogen and Ana Ramirez, Professor Ana Ramirez, showing their research between Colombia and the Netherlands. And finally, we have also Dr. Ximena Wartzman. Yeah, that's the one, correct. Go to the one previous, please. One more. Yes. Dr. Ximena Wartzman from Chile, presenting her research in clinical ultrasound developed in Chile. We also have some special panels planning to introduce the funding mechanisms and labs in Latin America. with the two Meet the Labs panels, and that we hope that this will help more and more people collaborate across different countries. In addition, we'll have the Women in Engineering with panelists from academia and in industry, where their career paths and opportunities will be discussed. And finally, we'll have several monetary awards for the best student paper and pitch competition. So please join us in this unique opportunity to network and increase the impact of Latin America in the society. And Andrea will put some, yeah, she did already, the link there so you can visit our website and see all the people involved in this. In the next slide, we have this opportunity, which is the creation of chapters. And this is another excellent opportunity for the for members of the UFFC society. And this chapters basically allow people to organize events and in a more local setting and other activities. And they the society sponsor these events. So please reach out to Dr. Lin Wei for more information. And then his email is in the chat box also. In the next slide, the UFFC Society is still accepting applications for the administrative committee. So please visit our website for more information and apply for volunteer work using the link in the chat. The next one, please. And if you missed any of our previous sessions, previous webinars, they are now available on YouTube, and this one is being recorded, will be there as well. So just go there and you can see and reach out to us if you have any questions or questions to the previous speakers. We will be glad to forward your questions. And if you want to join this webinar as a speaker, please let us know. Reach out to us. We'll be glad to consider you in here. And I will go now back to Sophie. Thank you all again and enjoy the talks.
Thank you, James. Hello, everyone. It's with great pleasure today that I'm going to introduce you to our first speaker, Benjamin Castañeda-Afán. Benjamin is actually a full professor of biomedical engineering and director of research and innovation in the Department of Engineering at the Pontificia Universidad Católica del Perú. He got his master's in computer engineering from Rochester Institute of Technology and then his PhD in electrical engineering from the University of Rochester. And after his PhD, he founded the Medical Imaging Laboratory in Peru. And he has more than 15 years of experience in biomedical ultrasound and medical imaging analysis. And Dr. Castañeda's research topics include quantitative elastographic imaging, computer-aided diagnosis tools, and telemedicine as well. So with that, I'll leave you to enjoy his talk. Thank you.
América Latina en Foco.
Hello, and thank you very much for inviting me to this presentation of the UFFC Society Outreach Initiative. My name is Benjamin Castañeda. I'm going to present about Tele-Ultrasound deployment in rural Peru. And this is a joint effort between Católica University, Medical Innovation and Technology, which is a Peruvian startup, and MIMAS, which is an NGO based on the US. Rural areas in Peru, as in many other countries of the world, suffer from different, very bad conditions in terms of the infrastructure and capacities in health centers. You can see here a typical health center in the jungle of Peru, some of its images inside, but you can see there's a general lack of infrastructure. And also this is located in a very remote location. You have to go there by boat, and it's probably around 12 hours from the closest hospital. Therefore, if you are talking about having diagnostic imaging in rural areas, this is a very difficult problem. Ultrasound, of course, is low cost, portable, It doesn't require any other infrastructure. So it's very suited to help in these underserved rural areas. But there are barriers to its use. There's a lack of high quality inexpensive scanners. But more than that, even worse than that, is that there's a lack of trained operators to acquire the images and trained image readers. And of course, you can think about telemedicine, but there's also a lack of communications infrastructure in these areas. I started thinking about rural areas in 2012 when we got a grant to build a Tele-Ultrasound scanner, portable device with specific conditions to help in rural areas. However, while doing this project, I came to understand that having the instrument, having the ultrasound scanner was one thing, but it is probably not the most important thing. Having people who can use this, enabling workers in the health centers right now to use ultrasound was then my main objective. Conventional tele-ultrasound, based on telemedicine, of course, uses the video from an ultrasound scanner, which is transmitted to the specialist, which is in another part of the world. And you can see here not only the video from the ultrasound scanner, but the application, how the transducer is held into, in this case, the pregnant woman. And the specialist can see both transmissions in real life. This is streaming in real life. And you can see here the operator in rural area also taking a look into whatever the specialist is saying. Again, another streaming in real life. So there are 3 videos being streamed out in real life, in real time, right? The problem that this is, of course, a very neat solution, but the problem with this is that it does have a high bandwidth requirement, and therefore it has a low penetration in most of the places in rural areas in Peru. You can only have this probably enough bandwidth and telecommunications infrastructure in Lima, which is the main city in Peru, and maybe in some other very few cities of Peru, but in the majority of places, in towns, and especially in a rural area, just as I showed you before, this is not possible. The other problem is that in trying to do this, it usually takes much more time of the specialist in ultrasound, which is a very inefficient use of human resources. Very likely, the radiologist or the specialist can do an ultrasound in 15 minutes if it's in situ, but using this conventional tele-ultrasound, probably it will take him or her around half an hour. And lastly, it does require a trained person. It does require that the operator knows how to do or perform a basic ultrasound being directed by the specialist. And the problem is when you have this person being trained, as soon as the person knows a little bit about ultrasound, the operator usually leaves the rural area and goes to a big city where he or she can get much more money for this acquired new skill. So therefore, it's not very scalable because you have to invest on training this operator for months, and afterwards they just leave the rural area. In this context, we're proposing a different model to perform tele-ultrasound, a synchronous model, which is more suitable for rural areas. In this case, there are 3 important key approaches to our model. The first one of them is to use volume sweep imaging or VSI protocols. Okay, so what's a VSI protocol? Well, you can take a look here of just a brief description of the protocols. It's a series of steps to acquire ultrasound volumes of a particular region of interest. In this case, this is the obstetric protocol. Okay, so you can take a look. The protocol is being performed here. It can be taught to people with no ultrasound background at all. No medical prior knowledge is needed. It's just a lot of basic movements of sweeps that goes around the person of the region of interest, and arcs that allows to have a better visibility of the region of interest. So the operators are trained to use these basic movements very quickly. So in a matter of minutes, they can learn all the steps required for an OB protocol, for example. There are 8 steps in the OB protocol. And again, this is just a basic movement of a sweep and then finishes with an arc. Okay? So training a person how to do OB ultrasound may take months, may take years, but to train a person into performing this type of movements is quite simple. Again, in 20 or 30 minutes, the person will know how to do it. Then we usually require the person to keep on training for another 8 hours in the span of 2 or 3 days. So they learn, they develop this motor memory on their hands and on how to perform this, so they do not forget. We have developed protocols such as these, BSI protocols for OB, for thyroid, for gallbladder, for lung, and now we're currently working on the breast one. So this is a very key part of our model. Being able to perform these protocols allows that our tele-ultrasound becomes asynchronous. The acquisition is then, therefore, using these protocols and does not need a radiologist or a specialist at that very moment. The other approach that is very important is the technological one, right? We use a tablet called the medical box that attaches to any ultrasound machine. And this tablet tries to encapsulate all the difficulties of using an ultrasound scanner. So you see that the rural area operators take a look into the ultrasound scanner and they say, oh, this is very much complicated. So they will learn very basic things about how to turn on and how to apply some presets to the ultrasound scanner, but most of their interaction is performed with a medical box. Therefore, we have this Windows tablet, it's a rack Windows tablet, so it can go to the jungle without any problem. It has a very user-friendly graphic user interface, saves basic electronic health record information, connects to the ultrasound scanner via DICOM or via VGI ports, video ports. And the ultrasound guides the operation on how to perform these sweeps and these steps of the BSI protocols. Then it is in charge of compressing, encrypting, and transmitting all this data to the cloud. And if there's no connection at this very moment of internet connection, then it stores everything in the hard drive. And whenever it is connected to the internet, it will send everything to the cloud. So therefore, having a slow internet connection, having no internet at the moment of acquisition is okay. It is possible still to perform this type of asynchronous ultrasound. So this is a comparison between conventional ultrasound, right, with the radiologist to the left, looking at the images, and according to what she is looking at, she's moving her hand and finding the right image in order to provide the diagnosis. In this case, we have an operator, which is almost no ultrasound training, who is focused on performing perfectly the best as she can to perform the BSI step, right? Take a look, she's not looking at the image, she does not understand the image, she doesn't need to understand the image. So she is performing these steps, and all her attention is on how to do these steps. And you can see the medical boxes here connected to the ultrasound machine. So this is a I think graphically describes the difference between conventional ultrasound and asynchronous ultrasound. And of course, the next part or of our approach is the software, right? We have an administration software in which we can follow everything being performed with medical boxes. You have up to 8, in this case, you can see the number of users, how many protocols, you can have OB, gallbladder, chest, so on and so forth, how many tablets you have in a particular deployment, how many studies have been performed. You can do a follow-up of the studies. Of course, once you have a new case, you can assign this case to another, to a particular radiologist anywhere in the world, where he or she will perform this reading. You can see all the information about the medical box, you can see all the videos, so you can give a second opinion. And of course, you have the electronic health record of the person. And of course, you will get here a PDF with a report once the radiologist or the specialist has taken a look at it. On the side of the specialist, ultrasound specialist, we will install software that will automatically keep tracking on what cases have been assigned to this particular specialist. Once a case has been assigned to him or her, the software, which usually runs in the background of the computer, will start downloading all the information. And when all the sweeps, for example, for an OB case, you have 8 sweeps, have been downloaded, and they are locally available to the physician, they will send a message to the physician saying, you have a new case ready for you to read. And once you double click on that case, it will open a DICOM reader. It could be the one that we install, or if the physician has his own preference of DICOM readers, that's okay. We have developed our own also. And once in here, it's just like it's using a software that the radiologist is very much used to it. And in these cases, we're sort of comparing what we are doing between ultrasound, comparing a volume. So we are giving the specialist a volume to go through, and in that volume understand what is the best, the image or the plane in which you want to take a better look, because there's some diagnostic information. So that is possible thanks to having all these sweeps that provides volume to the physician, very much to what the physician will do with MRI in an MRI volume or a CT volume. In this case, we have an image of OB protocol. Here we have the head, the fetus. This is a gallbladder protocol, but you can see the liver, most of the liver. It's actually an abdominal protocol. And once this is reviewed, you have between 6 to 8 sweeps or volumes that are available to the specialist to take a look. So there's a lot of redundancy built in those protocols. The specialist will fill in a structured report like the one you are looking in the screen. This is very important because it's much easier, faster for the physician or the specialist to fill in everything, but also in each step that the physician inputs, we will also record the confidence level of the findings that he or she are fine, right? So this allows to have some quality control on the operator, and also having this type of reports is very easy to then share with other physicians if you need to have a second opinion. In this particular report, we have a case of placenta previa, which was referred into Cusco's Regional Hospital, and very much likely saving a life, and definitely avoiding an emergency at the moment of birth. We tested this We started with this, testing this idea of asynchronous ultrasound with a pilot inside a Catholic university. We tested over 6 weeks, and we had 21 thyroid scans and 26 gallbladders. This allows us to tweak all the to tweak the whole system and verify that it works very well. And once we finish with this, we move to a real-life testing and real-life scenario in Leoncio Prado, in the rainforest of Peru. This is the place in which I took the images at the beginning, so it's 12 hours from the closest hospital. We have another 6-week testing period, where 16 pregnant women were scanned. So we had very good results over this period. In this area, we found that one case of placenta previa. We've implemented this all over Peru since then. Over 9 sites have been implemented, over 800 patients have been scanned. Usually it takes us 8 hours to train people. And we have more than 30 people or healthcare personnel all over Peru being trained with these ideas. This is a Repsol case. It's a particular one. It's a health center called Nuevo Mundo. And it was funded by Repsol, which is an oil company. And the interesting part about this is that the health center didn't have access to internet or to electricity for that matter. But we were able to run 74 diagnostics here, ultrasound diagnostics, based on the idea that we don't require power, everything works with batteries. So we will go there in the morning, acquire 25 cases, go back to our camp, which was inside Repsol's camp, it was about 1 hour and a half maybe, and we got internet there. The images and everything, all the 25 cases were uploaded to the cloud, and from there were read at night, and for the next morning we will come back with all the reports that the specialist was able to perform overnight. So we continued this over several days to have the 74 diagnostics. Because this implementation has received a lot of awards from the Ministry of Production in Peru, Innovative Industry Award by another university, UPC here in Peru, and we were selected by Israel's embassy to represent Peru in Tel Aviv, startup Tel Aviv. We've been working since then on AI, using AI for helping. What happens when you don't have internet? That's one of our main concerns. Or sometimes you cannot wait until the next day to have some of the results. So AI, I think it will help a lot to do some sort of a screening, tell us when the patient needs to go definitely to the hospital and when not to. So we've been having these initial results, and also for lung, again to detect B-lines and to detect conglomerates of pneumonia. So most of what I've been presenting that have been already published in Journal of Ultrasound in Medicine. We have our Tele-Ultrasound system, which was successfully implemented in a controlled environment at the university, but then implemented in different sites in Peru, the test in the rainforest and the highlands. With most information of that we've gathered from thyroid, from the abdominal or gallbladder protocol, and from the OB protocol, but we've been running other pilots or studies with a lung protocol, so we hope to have those results ready sometime soon. We believe that this system may help improve the health of millions of people in underserved areas. And we are currently working on AI, virtual reality. We've finished a series of comparisons between conventional ultrasound and asynchronous ultrasound. And of course, we're working on developing new BSI protocols for other medical applications, and in 3D volume reconstruction. Thank you so much for your attention, and I'd be happy to answer questions.
So thank you, Benjamin, for a really interesting talk. We're going to take all questions at the very end. So please post your questions in the chat in the meantime, and you can do this in Spanish, English, or Portuguese. And in the meantime, I'm going to introduce our second speakers, and we have two speakers, Eduardo Costa and Amanda Martinez. Now, Eduardo Costa received his bachelor's in electrical engineering from the University of Sao Paulo in 1978, his master's in biomedical engineering from the University of Campinas, and then his PhD in medical engineering and physics from King's College London in the UK. He's now a full-time professor at the Department of Electronics and Biomedical Engineering at the School of Electrical and Computer Engineering at the Universidad of Campinas. Amanda Martinez got her bachelor's in electronic engineering from the Federal Technological University of Paraná in 2016, and then her master's in biomedical engineering from the University of Campinas, and she's currently doing a PhD there in biomedical engineering. She's mostly interested in ultrasound technology for medical and biological applications, and she's very interested in the development of biomedical instrumentation as well. So with that, I'll let you enjoy their talks. Thank you.
Thank you very much, Amanda. Good afternoon, everyone. Thank you very much for listening to our talk. I, first of all, want to apologize. I have some difficulties in hearing and seeing, but Amanda is here to help me. I would like to thank Hermes Kamimura for the invitation, and all his team that is working in this Latin America in Foco. And I think that you'll be pleased to know that we have a very strong group in Brazil working on ultrasound research in several ways. We have created the RBTU, in Portuguese is Rede Brasileira de Técnicas de Ultrassom. Was the first name that appeared to us, that it was interesting. And today we are going to present the development of the Brazilian platform for ultrasound research. It was a joint effort. And I'm having the help and co-authorship with Amanda Martinez, our PhD student here at UNICAMP. I'm with the Department of Electronics and Biomedical Engineering, and also I'm an associate research with the Center for Biomedical Engineering. Next, please. Well, our network, the Brazilian network for ultrasound techniques, is composed of UNICAMP, several universities, UNICAMP, University of Campinas. We have the University of São Paulo, USP, in two groups. One is in São Paulo, in the Department of Mechatronics and Mechanics Systems, and the other is in the Department of Physics at the city of Ribeirão Preto. We have also a group at the Federal Technological University of Paraná, and another group at the Federal University of São Carlos, a group in the University of Rio de Janeiro, and our technical group is the researchers and engineers of the Research Institute, Eldorado Research Institute. And we have also the collaboration and as full partners in this network from INCOR, Instituto do Coração, Heart Institute of the Faculty of Medicine of the University of São Paulo. Next. Well, these 5 universities and the research institute, the Eldorado Institute, have been contacted by the Ministry of Health in the Department of Development and Innovations of the Ministry of Health there in 2007, 2008, to create a network and be able to get the knowledge and the know-how of doing a whole ultrasound machine, including transducers. The network was then created, and I am next, please, yes. And I'm the scientific coordinator. Go back one, please. Thank you. Vera Bouton was, she is already retired. It was our team, of course, with the students. At the University of São Paulo, Professor Júlio César Adamovski, already retired. Flávio Buioc and Pai Chinan. Pai Chinan get into the group later after the network was already created. And the Ribeirão Preto campus, it was Antônio Adilton Carneiro, and that works on elastography. Next. At the Technological Federal University of Paraná, Professor Joaquim Miguel Maia, Fábio Schneider, and Amaury Assef, that also get into the network later on this network. At the Federal University of Rio de Janeiro, we have Wagner Coelho and Marco Antonio von Kruger, and at the Federal University of São Carlos, José Antônio Eiras. In these groups, at UTFPR, it's an electronics group. At UFRJ, Wagner Coelho and Marco Antonio von Kruger worked on image processing and ultrasound phantom. At UFSCar, José Antônio Eiras worked on transducers, development transducers. Can you go back one? Júlio Adamovski, Flávio Buioc worked on transducers as well, and Pai Chinan on electronics, as well as myself and Vera Bouton. And Adilton worked on elastography. Next two, please. At the INCOR, Marco Antonio Gutierrez and Marina were working on cardiac applications for ultrasound research. And the Eldorado Institute, we have Eduardo Bertudo, that was the technical executive coordinator of the network. Haroldo Nisto was the project leader, and Guilherme Fonseca, the project manager, and we had along the development more than 25 hardware and software engineers and technical staff of Eldorado working on this platform. Next, please. We had two platforms. The first platform, you can see here the transmission, receiver, synchronism boards, and all these boards were huge. We were trying to develop something, and then we didn't know all the electronics problems that we could have. Then we have opted for this huge platform. Next. The platform attending to the contract with the Ministry of Health had to be ready by about 2012, 2013. And we then presented the platform. You can see the platform here in this left-hand side. Without Dr. Daniela, that was our clinical doctor, and then she learned the platform in less than an afternoon, during the afternoon of one day, and was able to use it. At the left-hand side, you have Haroldo Nisto and myself, and these are the teams. Santiago Rodrigues was the main electronics developer, and near to me there's Tiago Desotti and Johannes. They are experts in FPGA control. Here is just another for the right-hand side, Dr. Daniela examining one of the engineers here, right? His heart. Next. We have presented this in a Ministry of Health meeting, innovation meeting. Just in the center, it was the Ministry of Health at that time, in December of 2013, Ministro Alexandre Padilha. And after the first platform, we went on to change something, because next, the first platform was based on Virtex 6 FPGAs, very expensive, where the hardware was not optimized and very costly. At the end, we had almost $50K cost for one single platform. And it was due to the constraints to create the equipment in less than 2 years. We have to pose some constraints, and we had a very low flexibility in changing things in the platform, because we kept the hardware very tight. Next. These are one of the transducers we had created or we have produced. This is a 64 elements, 5 megahertz transducer, linear transducer, developed at USP in São Paulo. Next. And these two other transducers were developed by José Antônio Eiras and Luiz Vassora at the Federal University of São Carlos. One is 3.5 megahertz, and the other is a 5 megahertz PMN transducers at the right. Next. Well, the second platform was based on another FPGAs, very much cheaper, optimized the hardware. We had a total cost for one platform of $10,000. Very flexible compared to the other one. We can get the RF data, changing imaging modalities and create new modalities, right? And it still need to attend the Minister of Health contract, and we had to produce a B mode, Doppler mode, and M mode imaging. Next. This is the main look of the platform, an overview. It is based on one personal computer with a GPU processing board, and there is an interface that will send the configuration data for the control and sync modules that will control the transmission and the reception on the receiver boards. And there is a multiplex board that is connected to the transducers, because we can use 64 element or 128 element transducers, and all connected with a backplane. Next. This is just an overview of the data flow. In the computer, we have the software. All data the images are produced with the GPU board. Then all data is processed in the computer, and the data flow goes into the user configuration, goes into the boards until reaching the transducers. We use the data, A to D converter goes into the receiver board, right? And with two 3.0 interfaces, USB interfaces, we are able to get all the RF data for all frames to be processed in the personal computer. Next. Well, here I turned over to Amanda, that will be able then to explain with a bit more information from here. I'll return it soon. Thank you. Amanda?
Thank you, Professor. So on the receiver board, the analog front-end components use 12-bit analog to digital converter. This device provides at its output 8 digital data channels, a clock signal for data synchronization, and a clock signal for delimiting the start and end of a data frame. Data is sent over the data channels in serial form. The analog front end sends a valid data at each rise and fall of the data clock. The rising edge of the frame clock signal indicates the start of a new data set. In our design, there are 32 data channels for each receiver board. The serial data sent by each analog front end are organized in parallel 12-bit words and sent to the FIFO module according to the control signals signalizing frame construction. The formed 12-bit word are mounted in a 16-bit format to be sent to the delay and sum module. In our project, the analog front-end components were configured to provide the data using choose complement notation. For each analog front-end, a FIFO memory was created. Data clock signal of each analog front-end is used to write in the respective FIFO memory. Thus, the data writing operation in each FIFO memory occurs at independent times, since each FIFO has its individual data clock signal. However, reading data from FIFO memories uses the same clock signal. Thus, the FIFO's read operation occurs simultaneously as they share the same clock signal. In our design, this common clock signal has a frequency of 100 megahertz. Thus, FIFO memories serves as delimiters between different clock domains, and all data after the FIFOs belong to the same clock domain and are therefore operating on the same frequency. After all this process, it is possible to send the data to the delay and sum module. In the delay and sum stage, the data is being formed according to the delays configured by the user. And this module receives 32 data samples simultaneously, and after processing, a single 16-bit data sample is sent to the interface module. This interface links the platform hardware to the platform associated computer running the software for setup control and image formation. The interface module receives the data samples from the delay and sum module, groups them into packets, and sends them to the external computer through the USB 3.0 protocol. As there are two receiver boards, it is necessary two 3.0 USB interfaces available in the personal computer. In our research group, we are carrying on research on plane wave imaging. In order to do that, it will be necessary to implement it in our platform. First, we are going to implement it to be able to transmit and acquire ultrasound data at high frame rates and process it offline. And after that, our goal will be implemented in real time. For the transmission circuit, we are already capable of transmit plane waves with normal incidence and different deflection angles with a high frame rate. For the reception, we have removed the delay and sum module, and due to the huge amount of data, we shall store it in an external DDR3, and we are modifying the USB 3.0 interface module. In figure A, we are showing the original reception firmware of the RBTU platform, and in B, the reception firmware with modifications to plane wave imaging. Here we show an image of the reception board project and a picture of the board. Yellow rectangles indicate the FPGAs in the project, and in the photograph, the yellow rectangles indicates where the FPGA modules are going to be mounted. The red rectangles indicate the analog front-end components in both project and photograph. This photograph was taken while the platform was under development, and we can see the backplane board at the end of the platform. Here, there is an empty slot with the connector available to receive another transmission and receiver board, indicated by the yellow rectangle here. The control and synchronism, one transmission and reception board, transducer and mux board are properly connected to the backplane. So this is the full setup: platform connection to the transducer, platform connection to the computer, and monitor for image visualization and user interface. With all on, we can zoom the interface to see more details of the graphical user interface, which has an option to send user settings, online parameter configuration, freeze the image, and define RF data acquisition. And here is the region where the image will be shown. And now I'm going to play a demonstration video about the RBTU platform. I just ask a few seconds while I adjust the microphone. Hello, this video is intended to show the RBTU platform and the main operating modes already implemented on it. The platform was developed based on a backplane architecture. All boards or modules of its hardware are inserted in a way to connect through the backplane. Each module is inserted into a slot in the cabinet. The source module, responsible for AC power input and DC power distribution for the entire platform. Sync module that receives configuration files and distributes them to other boards. Reception and transmission modules, where all components that make up the 64 channels are located. MUX and transducer module that have the components that make the multiplexing when necessary, and the connector for the transducer. Now, let's run the ultrasound imaging software on the platform's PC. Note that the generated image will be directly related to the chosen configuration file. Hardware and software have various degrees of freedom, and the user can configure these various parameters through a preset present in the configuration file, which is written according to JSON notation. The preset is a set of parameters that defines an operating regime, containing information for hardware and software configuration. We are going to explain it a little bit more. So, in hardware configurations, we must configure a label, in this case, B mode with a depth of 15 centimeters and focal point at 8 centimeters. We can also configure 4 different pulse formats, A, B, C, and D. In this case, for pulse format A, we will have 70 nanoseconds in minus 24 volts and 70 nanoseconds in 24 volts. If we want to, we can add more cycles like pulse format B. We can also change the duration and amplitude of voltage like pulse format C, or like pulse format D. In the software configurations, we will also configure a label that must be identical to the hardware configuration label. And we will have here a general configuration preset where we will choose which mode will be active, B mode, Doppler, M mode, or RF signals of one scanline displayed on the monitor. We will have the transducer specifications that can be linear or convex. These are the main presets of software and hardware configurations. We have chosen a configure file for B-mode imaging, and here we are showing a real-time imaging obtained with a convex transducer. Now we are showing a B-mode imaging obtained with a linear transducer. For this image, it was necessary a new configuration file. Through a slider line, it is possible to scan any B-mode scanline and show it over time as M mode, which has the same dynamic range and independent gain settings as B mode. It is possible to visualize a line in the time domain in a fixed region of the graphical interface. It is important to note that the visualized signal is in real time and has no processing or filter. The signal digitalized by the analog to digital converter, also called raw data or RF signal. It will be necessary to set the parameter line echo active equals to true in the configuration file. The RBTU platform can perform Doppler imaging. Here we are using a Doppler phantom in the laboratory, and it is possible to change the flow direction by clicking on a button.
As soon as we click on a button, the color of the region of interest of the image changes from red to blue and vice versa, just as one would expect. This indicates the correspondent flow direction changes. Thank you so much for your attention.
Now, Professor Eldorado is going to lead the end of this presentation.
Yes, we are deeply grateful to all colleagues that are in this network, Brazilian network. It was a great effort. We have been funded by the Ministry of the two agencies, FINEP and Fundo Nacional de Saúde, National Health Fund, and all linked to the Ministry of Health. And we are very much, we would like to thank people from Eldorado Research Institute for their effort and you all to listen to us. Thank you very much to everybody.
Thank you.
Thank you so much for that presentation, Amanda and Eduardo. I'd now like to introduce you to the technical moderator of our fourth webinar, Jean-Luc Jenison. He mainly developed the ultra-fast ultrasound imaging technique and especially the elastography technique to quantify the stiffness of biological tissue. He drove more than 15 clinical protocols on development. His work took the continuation of his PhD, which concerned a 1D ultrasound imaging device, the FibroScan, which is now commercialized by the company EchoSense and used for the clinical diagnosis of liver fibrosis. I would like to remind you again that questions can be typed in English, Portuguese, or Spanish. If you wish to speak, please raise your hand using the action button and wait for the moderator to unmute you. And without further ado, Jean-Luc.
Okay, thank you very much, Lacey, for the introduction. And I would like first to thank Hermes for the invitation and all the participants of this webinar. So I think we'll begin with Benjamin's talk. And we have some questions in the chat. And the first one comes from Chris de Kort in the Netherlands. And he says that it is very impressed by this work. And if Benjamin can answer directly, how far are you with all the different applications to do the analysis online using, for example, AI, artificial intelligence?
So we have already, besides the talk I just gave to you, we had a study we're just about to publish in terms of comparing BSI protocols or BSI application with in situ radiology. So we've taken part of that data to do an AI algorithm with very nice results. To your question, Chris, we are about to, or we are writing a protocol actually to do that prospectively. We currently have around 6 sites that are running this BSI acquisition and BSI technique. So we're hoping to start recollecting data prospectively on how good the AI is working, and of course, do a feedback to our algorithm to keep improving it. That was the plan before COVID-19. COVID-19 has, it slowed us down greatly. Now the focus is currently on BSI lung protocol rather than any other one. And about BSI protocol, we had our, we did with Roberto Lavarello, who's also here, some AI techniques a couple of years ago. So we are currently working on that. So generally speaking, we are I think we are going to be able to start collecting data and trying out our AI next year.
Thank you, Benjamin, for this answer. We took another question for you. The one is coming from Hermes Kamimura. How are the regulatory aspects for tele-ultrasound in Peru? As an example, in other countries, it is not possible to practice ultrasound if you are not a physician. So how do you deal with this aspect in Peru?
So regulatory issues are by far much worse than the technical ones. Solving something technical is much, much easier than the regulatory issues. So about that, in Peru, to perform such a thing like we're doing with tele-ultrasound, you need a healthcare personnel. There are some people in the College of Medicine here in Peru that are pushing that it can only be performed with another physician, but the reality is that we don't have enough physicians, so that has not been successful. So far, we can do it with health personnel, and everything you've seen or that I presented was work with health personnel from the health center. So far in that aspect, so far so good. This is, and also in terms of medical devices regulatory issues, this is not so far that is likely, this is likely going to change, but so far this is not considered a medical device. This is more considered a telecommunications device, as we are using a commercial ultrasound scanner to acquire the images and do the interaction with the patient.
Okay. Thank you, Benjamin, for your answers. I think we are short in time for many questions, so I will ask to Eduardo and Amanda another question about that talk. And it comes also from Hermes. What image modes and probe types are you currently available on your platform?
The platform has B mode, M mode, and Doppler mode, color Doppler, already installed. We have some files that just do them, but it is a very open and flexible platform. You can do any kind of imaging. We are trying to make it for plane wave fast imaging. There are some constraints that you have to program the receiver board, the FPGA in the receiver board. And this is Amanda's part of her PhD to work on that. But it's already available, 3 modes.
Okay.
If I answered everything.
Okay. And another question: what is the maximum number of channels you can have on your device?
Okay, right. The platform comes with 64 channel transmit receive. There is another slot for another 64 channel, but it is possible to make it bigger. It is modulated, and then you can add another modules, but you have then to change the whole the backplane and some parts of the platform, but you can add another 64 channel.
Okay. So 128 max. Okay, for now.
128 is the most now.
Okay, thank you.
But But if we have a 128 transducer, because we have a MUX multiplexer, we can do images with 128 element transducers.
Yeah, the first part and the second one after that. Okay.
Yeah.
Good. Thank you, Eduardo, Amanda, for your answers. Thank you, Benjamin, for the talk. And because we are running out of time, I would like to thank again the speakers today. I would like to thank also all the organizers of this webinar. And it's time to close the session. So thank you, everybody. Have a good day or have a good night like me.
Thank you. Thank you very much.
Bye.
Thank you everyone for joining us. And just a reminder as we wrap up that next month is the Latin America Ultrasonic Symposium that'll be taking place from 4th through 5th October, and we hope to see you there. So everyone have a great morning, afternoon, and evening, and thank you for joining us.
Thank you.
Thank you.
Thank you, everyone.